Thank you very much to the organizers for the invitation to speak at this wonderful conference in honor of Nigel. Every once in a while in one's life, one encounters something which you discover, is handed to you, and it transforms the way you look at the world. This happened to me when I was a teenager, and I heard John Coltrane's masterpiece, A Love Supreme. In fact, that work is a microcosm of the experience. It comes in 4 movements: acknowledgement, resolution, pursuance, and song. And at the end, you are left with inner peace. 10 years later, I had the same experience when I learned about the Higgs bundle moduli space. Here we find all of these structures interacting. There are these different algebraic varieties. There's a C-star action on one of them, but not on the other, and yet there's this magical transcendental isomorphism between them, which is mediated by Hodge theory. And I never understood why it was that I had the same experience when I listened to A Love Supreme as learning about the Higgs bundles. And then I learned from Woodmill on Monday the reason why. We were greeted by the holy trinity of Hodge theory. As he said, that Trinity is in the audience, and I hope I will be forgiven for the sins that I've done. So I'm very happy to have the opportunity to speak about this project. It's something which has been brewing since my time as a postdoc with Nigel. It's now a joint work with a former master's student, Aidan Lindberg, who's now a PhD student with Marco in Toronto, so another member of the family. And some of these themes that we see in Higgs bundles are actually going to reappear in a completely different way. It's not a perfect analogy, but maybe there's something to it. Okay, I'm going to speak about deformation quantization of smooth algebraic varieties X. So let's recall what that means. Deformation quantization of X is a formal deformation of the structure sheaf as a sheaf of associative algebras. So I start with the usual product, and then I start deforming it by adding a first order correction, a second order correction, and so on. And I get a formal power series of functions. And I require this star product to define for me an associative multiplication, which is linear over H-bar. And it has a semi-classical limit, which I get by looking at this algebra. Well, it's commutative when H-bar is equal to 0, is the ordinary product of functions. So the interesting thing to look at is the commutator at leading order in H-bar, which is the first derivative. So we skew symmetrize the product, we take a derivative, and what we get is a Poisson bracket. We've seen it now a couple times, but I'm going to code the Poisson bracket in a tensor. Sigma, it's a holomorphic section of wedge 2 of the tangent bubble, and it gives the bracket back by pairing sigma with the wedge 2. In this story, there's a very important role played by the possibility that the sheaf of algebras doesn't glue together properly anymore. There could be a jerk, or if you like, a B field in the generalized geometry language. I'm going to systematically sweep that under the rug. So the big theorem in the subject is Kontsevich's 1997 theorem, which says that every smooth Poisson manifold of variety has a canonical quantization. What does this look like? It's a new product. Again, it's a formal power series, but the interesting thing is that you have a coordinate system and it gives a formula for this product. It's a Feynman expansion in the style of physics. And so every term is a graph, and every graph gives you a coefficient, which is some kind of high-dimensional integral. In this case, it's an integral over the moduli space of Mark holomorphic disks. And then it gives some combinatorial recipe for taking derivatives of the functions involved and also the Poisson bracket in order to produce that term in the theory. So the coefficients, the Feynman integrals, are completely independent of f, g, and bracket. And then the combinatorial part is where all that data appears. So the coefficients are some kind of constants which you find once and for all, and they just keep the job. You can think of the graphs as like enumerating all the possible expressions you could write down, the derivatives of f, g, and bracket. So this is how the theorem is often described, but I want to emphasize an important point of this proof, which is that it proves something much stronger. Okay? So I want to think of it in the following way. So let's imagine that there's a moduli space of Poisson structures, Poisson varieties. So in that moduli space, I have a point, this blue point, which corresponds to x, equipped with a zero Poisson vector. And the moduli space is a kind of conical object, because if I have a Poisson bracket, I can multiply it by any number, and it will still be a Poisson bracket. Okay, so there's a kind of rescaling direction in this moduli space. That's the C star. And on the other hand, we have a moduli space of associative algebras. And inside of there, we have a point, which is the algebra of functions on the variety. And what Kontsevich observes is that these moduli spaces, if you zoom in on these 2 points, look the same. More precisely, the one on the left is the tangent cone of the one on the right. And then what he does is to construct a map, which we'll call the quantization map, which takes a Poisson structure and produces an algebra. And there's a formal power series, so strictly speaking, what you get is an isomorphism of the formal neighborhoods of these 2 points. Okay, but so it's some kind of transcendental thing, thing by infinite series in general. And the way he does this precisely is to analyze the differential gradient Lie algebras that govern these deformation problems and prove that there's a homotopy equivalency. So now, how do we connect this with the original picture of a star product, which just has one parameter of h bar? Well, we use the conical nature of the space of Poisson structure. So I fix a Poisson structure, and I consider the ray, which goes off to infinity, rescaling sigma by the parameter h bar. When I map that over to the other side, I will get some path in the space of associative algebras, and that is the canonical quantization. In general, quantization just refers to some kind of path coming out of OX. And if I go over to the left, it may not be a straight line, it could be some curvy thing. The canonical quantization is when you have a straight line in the space of Poisson. All right, so there are many questions about this process which are still open. You handed a power series, the first thing you want to know is whether it converges. We don't know. Probably most of the time it doesn't. But if it does, you can ask if you can calculate the sum. If it doesn't, you may try to resum it using these new methods of resurgence. And there's another thing here, which is that the formula is not the unique solution to the problem. Shortly after Kontsevich proved the theorem, Tomarkin proved it in another way, which revealed that there was secretly a choice being made, which is essentially a choice of the Feynman rules, which define the Feynman integrals that you're supposed to count. It turned out that there are actually many different possible Feynman rules to define these integrals, whole infinite dimensional space of choices, in fact. And then you can ask whether the algebra that you get out of the process depends up to isomorphism on the choice of Feynman rules. So given this freedom, maybe trying to calculate the star product on the nose is not the right question, and what you should try to do is calculate the algebra up to isomorphism. So for instance, you may try to find the generators and relations presentation of the algebra, which makes it clear which algebra it actually is. Okay, so that is going to look like an algebra which is generated by the coordinate functions, and then the commutators, which would normally be 0 for a commutative algebra, get deformed by some expression which depends on the input. So let me give some examples. So the easiest case is when you take x to be the plane, or in other words, the cotangent bundle of the line, and then the standard Poisson bracket is given by the canonical recipe, q brackets p is equal to 1. And so when you quantize this, you can sit down with the formula and you can actually compute all the terms that you need to find the star product of these two functions. There are actually not very many terms. Because as I said, you have to take derivatives of the functions. Here, there aren't many derivatives you can take of linear and constant functions. So you can just completely write down. It recovers this Moyal star product, which is known for all time. And well, that algebra is isomorphic to the so-called canonical commutation relations. So the commutator gets shifted by a constant. So in other words, it's the differential operators. Okay, the next case to consider is when we have brackets which are linear in coordinate functions. Now you can play the same game. It turns out that you can calculate enough terms in the series to figure out exactly what it's doing when you multiply the polynomial functions. And you discover that, well, basically the same thing happens. So the commutator becomes the Poisson graph for linear. So what's happening here is that the linear functions form a Lie algebra. So the space is the dual of the Lie algebra, the standard Lie Poisson structure. And when you quantize it, you get to the universal enveloping algebra of this field. Okay, quadratic. Now all hell breaks loose. The series is definitely infinite. There seems to be no obvious way to calculate the term. So here's the simplest quadratic bracket where something interesting happens. The bracket of x and y is x times y. What happens, one thing that you can see for sure is that when you multiply x and y, what you're going to get is some function of h bar times the ordinary product of x and y. The reason for that is that the quantization formula is equivariant for linear change of coordinates. So if you have something which is x times y before, it has to say x times y. Okay, but there's a kind of symmetry here, or kind of anti-symmetry, which is that if you multiply in two different orders, the coefficient that you put in front of the ordinary product changes by flipping h and minus a. Okay, so you want to figure out what this algebra is, what you have to compute is the series S of h. Here it is. 1, 2, h squared of 24, etc. And here's the Riemann zeta. So I can't resist but to give you one slide about the coefficients in the formula. The coefficients in the formula. Okay, so we just saw zeta 3 squared over pi to the power of 6. And you may remember a beautiful formula of Euler, which says that the 2nth value of zeta is a rational multiple of 2 pi to the power 2n. Okay, so then, well, if we go back, actually, there was a zeta 3 squared over pi to the 6. That looks like maybe it's going to be rational. However, the conjecture is that it couldn't be further from the case. So pi, zeta 3, zeta 5, all the odd zetas are expected to be algebraically dependent over Q. So they satisfy no polynomial relations. This is supported by a mountain of numerical and conceptual evidence from the theory of motion. In fact, these kinds of numbers are exactly what are always going to occur when you compute a star product. So these universal coefficients we proved a few years ago are linear combinations of the so-called multiple zeta values, which are generalizations of the special values of the mean system. That was work with Peter Banks, who wrote the code that allowed me to compute the star product of the previous slide, and Eric Panzer, who also wrote some of it, but so the lengthy collaboration. Okay, so the upshot is that we have an algorithm which can compute the star products symbolically to all orders in H. But the problem is that the formula that I showed you on the last slide is something like 50,000 Feynman graphs were added up to get it. If you go to H bar to the 7, there's way too many, and it's kind of not worth it. But anyway, let's think about this a little bit more. So this is Kontsevich's original Feynman rules, the formula from the previous slide. And now, as I said, there are other rules. There's only one other explicit one that I'm aware of, which was also explained by Kontsevich and later proven rigorously by Alexeyev, Torus, Rossi, and Bill Bacher. If you change the Feynman rules, then something interesting happens. You get another power series, which is the same up to the h bar cubed. That's actually always going to be the case. And then at h bar to the 4, something changes, and actually by the time you get to h to the 6, things look very different. There's no zeta 3 squared. Okay, so that's what I mean by saying that it's probably not a reasonable thing to try and compute the star product directly and get an answer. It seems like it's not meaningful invariant quantity. But what we can try to calculate is the defining relation. So x star y, as we saw, is the same as y star x up to a factor. That factor is a series, which is the ratio of s of h divided by s of minus h. And so we can calculate that. 1 plus h, that should be an h squared over 2, excuse me. H cubed over 3 factorial, h to, oh boy, I really screwed up my powers, okay. You see where this is going. If the exponents were right, you know what that means. And indeed, this is a theorem. This series, Q, will always be e to the h to all orders of h. Okay, so my job for the talk is to explain this out. So I want to advertise a viewpoint, which is that in many, many quantization problems, a similar thing occurs where the quantization is some kind of exponentiation of the Poisson structure. So this happens, or is at least expected to happen, for instance, with cluster algebras, which actually look locally like this bracket we were already looking at. And therefore, by extension, character varieties, quantum groups. Another case is the moduli space of bundles, certain types of bundles on elliptic curves, where there's a beautiful Poisson structure, which is described by Fagan and Odesky, building on Morphoskoriana. For certain type of moduli bundles on the elliptic curve, the moduli space is a projective space. And it carries a natural Poisson structure. And there's a formula for its quantization, written explicitly in terms of theta functions, which seems like a kind of magical cancellation of terms and everything that has to work out in order to make that algebra work. But the key feature is that there's a quantum parameter which plays the role of Q in the previous slide. But rather than being e to the h, which would be a non-zero complex number, now this quantum parameter lives in a group, which is not C star, it's the automorphism group of this elliptic curve, more precisely the connected component. And so you can think of Q as being the exponentiation of a vector field on the curve, which you can extract from the Poisson curve. It's called the moduli. So when you write that down, you will see that writing down that automorphism, that translation of the curve in a projective embedding is, of course, going to give you some expression of all that data. Many of these examples are Poisson final manifolds or closely related to such. And I have the suspicion that what's going on here is some kind of quantization principles for Poisson manifolds. So the question is, why do we keep seeing this exponentiation occurring in the quantum parameter? So Kontsevich proposed a method to study this problem. He gave the 2008 Lefschetz Memorial Lectures, and Ernesto wrote some very nice lecture notes, where a kind of plan was described. Okay? So let's revisit our picture. I'm going to paraphrase what's in that paper because I think it's the message that you get when you read between the lines. So we have our two moduli spaces, the Poisson structures and the noncommutative algebras, and we're trying to understand this quantization map. And maybe one of the reasons it's difficult to describe this map is that you're trying to calculate things in the wrong coordinates. So perhaps it would be advantageous to construct natural coordinates on these moduli spaces in which the quantization map becomes simpler. And the method proposed is Hodge theory. So what we're going to do is we're going to construct canonical coordinates on the moduli space by mapping to the moduli space of mixed Hodge structures. So we'll have some period maps. One will take a Poisson variety and construct a mixed Hodge structure. And the other one will take a noncommutative variety, if you like, and construct its mixed Hodge structure. And this is going to be done in such a way that the triangle is commutative. So that means that if these period maps are at least locally injected, so in other words, the local Torelli property, then we can compute the quantization by going the other way in the diagram. Down and back. Make sense? Okay, so that's my job, is to describe for you what these period maps are supposed to look. By the way, it's of course not guaranteed that the period maps will be injected. There will be lots of examples where it's not. But the curious thing is that in those examples I put on the previous slide, it does seem that it is injected. Okay. So I know there are many experts on Hodge theory in the audience, but I'm going to quickly remind you about mixed Hodge structures, both just to set some notation and also because there are some subtle technical issues which we need to overcome. So I need to explain where those are coming. So Deline, building on the work of many people, explained that if you have any variety of complex numbers, the cohomology of that variety carries a linear algebraic structure called a mixed Hodge structure. So this is a bunch of data, which I'm just going to call cohomology of X, but it's a receptacle for many things. So the first piece of data is called the Betti datum. It's an abelian group. Okay. So there's no abstract notion of mixed Hodge vector, which is a linear algebraic notion. And then there's this concrete realization when you have a variety. In this case, the abelian group is going to be a singular homology of the complex points of the analytic topology. There's a complex vector space, which is called the Durand datum. Okay, and that's going to be the algebraic Durand homology. Well, these two things, by Durand's theorem and Grothendieck's generalization thereof, are related by a so-called comparison isomorphism, which is the standard integration isomorphism between singular and Durand homology. And then the real magic comes from the fact that when you have a variety, I mean, all of this structure is basically present for any smooth manifold. When you have a variety, there are two additional pieces of the weight filtration, which is an increasing filtration on the rationalization of the Betti. This is somehow encoding some subtle topological features of the variety. And there's the Hodge filtration, which is a decreasing filtration, which is more of a transcendental. And these have to satisfy an axiom called the opposedness axiom, which says that if I take the associated graded, the weight filtration, then what I get gets decomposed into HPQs, where P plus Q is equals K, the weight. Okay? And the filtration F is what does the job. And it's complex conjugate. Complex conjugate makes sense because so F lives on the Durand space, but it's the complexification of a rational space, so it has a complex conjugate. Okay, so that's the mixed Hodge structure. And the way that it's constructed when X is smooth is as follows. So first of all, if X is compact, so say projective, smooth projective variety, then this is just the classical Hodge decomposition. So the thing you need to sort out is the non-compact case. So what you do is you want to make use of classical Hodge theory, so you compactify by adding a normal crossings divisor at infinity. So you get a smooth variety. And then you take the dynamic cohomology and you observe that it's the same as the cohomology of the different complex of forms, which is the forms on the compactification which have log poles along the boundary. Okay, and now you get the wave filtration by essentially looking at what the boundary stratification does to the cohomology, spectral sequence. And you get the Hodge filtration by truncating the complex of the logarithmic forms. This is different from truncating the form with arbitrary things. Very important. Now, the reason I've gone through the trouble with this excruciating detail of definitions that Marco complained about the other day is that the very existence and the uniqueness of this mixed Hodge structure rely on resolution of singularities. Because you need to compactify X. So first of all, you have Nagata's theorem, which tells you can find some compactification, but it might be singular. So then Hironaka allows you to resolve getting X bar to be smooth and the boundary to be normal crossings. Okay, but now you've made a choice in order to define W and F, and you need to check that W and F are actually independent of that choice. And so the way you do that is to suppose you have two compactifications, you find a third one which dominates them, and then if you have a map of compactification, it's kind of clear that the structures are isomorphic. So you can connect all your compactifications by a zigzag of maps, then you're safe. But to construct that zigzag, you also need to resolve singularities. So both existence and uniqueness rely on resolution. So now I have to explain another issue, which is that in noncommutative geometry, you have a noncommutative algebra, there's no space. It's not functions on a space. You don't know what a simplex in the space is, so you don't know what singular cohomology means. But there is something that does make sense, which is K theory, specifically topological K theory. So let's recall the idea of topological K theory is a generalized cohomology theory whose zeroth cohomology is the Grothendieck group of continuous vector bundles in space. Vector bundles have a Chern character. And so this cohomology theory comes equipped with a map to singular cohomology. But the Chern character is a mixed degree class. And so what you really get is a map to the two periodization of the singular cohomology. So even or odd. And what they proved using the famous Satilo-Herzog spectral sequence is that this map becomes an isomorphism after tensing with the Q. Now there's a subtlety here, which I have to admit confused me for a lot longer than it should have. I was making all these calculations, nothing was working correctly. And then I realized a very standard fact, which is that the Chern character of a vector bundle is not a rational class. It has powers of 2 pi I, right? So the first Chern class, you should not think of it as an integral class. You should think that it's a 2 pi I position coming from the exponential sequence. So that means that in this map, one should really insert the so-called K-twist, where powers of 2 pi I are added into the game, but every time you multiply by I, it's going to also involve changing the way you define the Hodge and wave filtrations so that the PQ indices get shifted down by 1. So say you had a compact Kähler surface. Well, here's the picture of its even cohomology. Okay, so the even cohomology is a diamond. You have the usual HPQs. So the wave filtration is going up. P plus Q is the wave. Right? So I have 0, 2, and 4. And the Hodge filtration is the P index. So I've shaded it here. So the lightest shading is the smallest part of the filtration. Then the medium shading is the middle part, and then you have the F0, which is there. But when you insert all these K-twists, what happens is that PQs get shifted down by the number of K-twists, which means that you get this picture. Now everything in the middle of the diamond is placed in 0, 0. The stuff on the left becomes 1, minus 1, which looks a bit funny, but it's fair game. And on the right, you have minus 1, 1. And now the Hodge filtration goes to the right, and the weight filtration has disappeared. Everything is 1, 0. It's a bit strange, but that's the thing. And actually, you know this from generalized geometry in a completely different perspective. So if you think of a complex manifold as a generalized complex manifold, and you look at the natural Hodge decomposition that was studied by Marco and by Gilles Cavalcanti, this is the decomposition that we get. Okay, and another subtlety is that the comparison between K-theory and Betti cohomology is actually not the term character, because that is not compatible with Poincaré duality. There's a Riemann-Roch correction, which tells you that you should twist the Chern character by the square root of any half-twist. And actually, you can twist it by different things. For instance, there's this thing called the gamma class, which is a hot topic. It also satisfies the Riemann-Roch property. So there are different things you can put for a hat here. And that corresponds, in fact, to changing the Feynman rules, which you're going to use in the quantizations. Very interesting question, which I have been completely unable to solve, is how the Hodge structures that I'm going to define for you depend on this choice of the comparison. Okay, so now I have to explain what to do when you have a Poisson variety. So we're going to start with the Poisson variety X, a smooth one, and we're going to try to associate a Hodge structure. So the ideal thing to have as the input is just a variety. Okay? But the problem is that to do Hodge theory, you need to be able to resolve singularities, and that is a fundamentally obstructed process in Poisson geometry. There are Poisson varieties that do not admit Poisson resolutions, even if they're these so-called symplectic varieties that are quite popular in the representation theory community. So you're going to have to scale back your ambition and work with things which have been resolved until we find a replacement for resolution singularity in this one. Yes.
Is it possible that the mixed Hodge modules might, in the Hodge theory filtration, might be able to work without resolution?
I would love for that to be true. But at the end of the day, that theory somehow, I think it also sort of relies on resolution at some point.
Well, it serves as maybe, but it would rely on left-sided pencils, and then you don't have those.
Yeah, that's a good question. I'm not sure. It would be great if that could solve the problem. So I'm going to scale back my ambition, and what I'm going to use actually as input is what I'll, for the lack of a better term, call a smooth log Poisson variety. So what is that? It's the following data: a compact scalar manifold, X bar, which will play the role of a chosen compactification. I'll have a holomorphic Poisson structure on the compactification. And I'll have a boundary divisor, which is a normal cross divisor. So that's the data. It's this triple of the compact thing, the Poisson structure, and the boundary divisor. But I want you to think of this as an avatar or a model for the open part, which is the complement. So for instance, when we talk about a morphism between such objects, we should look at maps of compactifications which send interiors to interiors. So think of that as a compactification of a map. And then what you're going to want is that anything you do is invariant when the interiors are identical. So there's a kind of weak notion of isomorphism, which is not strictly an isomorphism, but it's an isomorphism in the interior. You want everything that you do to be independent of, so invariant under weak equivalence. Okay, so some examples. So these brackets that we saw early on are examples of the so-called log canonical brackets, where the bracket of two coordinate functions is the scalar multiple of the product. So how can we think about those? Well, this Poisson structure is invariant under the torus action, which dilates the coordinates. And so in fact, we could think of it as not living on Cn, but living on C star to the n, where it defines a torus invariant structure. So then that kind of suggests an obvious compactification, which is to take any smooth projective to our plan. So for the one we're looking at before, it's two-dimensional, we'll take P2 as a example. So these are the structures that Vesti was talking about. Another example would be to take a compact Poisson surface. You alluded to those as well. So this is just a compact surface equipped with a section of an anticanonical bundle. So it has a divisor naturally, which is the anticanonical divisor on which the Poisson structure vanishes. Now, of course, that need not be a normal process divisor, but you could, in this case, blow up until the singularities. But for instance, if you have a smooth curve in P2, it will be elliptic. More generally, an interesting class is the Poisson-Fano varieties. So Y is a Fano variety, smooth, and sigma is a Poisson structure. There's an interesting conjecture about the structure of these objects, Victor von Dahl. What he predicts, so a part of the conjecture, is that the zero locus of the Poisson structure always contains a curve. This is a very surprising conjecture because you just count the number of equations for the zero locus, it's way, way more than you would expect to get a curve. This conjecture is known up to dimension 4. Beyond that, we don't know. But here's an example. So here's a very nice Poisson structure on P3. It has a curve, which is a plane cubic as its zero locus. And the symplectic leaves of this Poisson structure, they form a pencil of cubic surfaces, which hit the plane. So the triple plane is part of the pencil. And the base locus is a curve. And the zero set of the Poisson structure is that curve, and then I think it's 8 locus. Okay, so what I'd like to do is consider the complement of this curve as my primary geometric object, which is going to be a useful thing for the period map. But the problem is, you see, the curve is not a normal process divisor, it doesn't have the right dimension. So what you're going to have to do is blow up the curve and take the exceptional divisor. And now you have a smooth threefold in this case with a divisor whose complement is the same as the complement of the curve in the original threefold. Now, of course, the curve itself may not be smooth in general, so there's going to be a further issue resolving the singularity of C before you blow it up to get this logarithmic model. But anyways. I should give you some things that don't work, so you can see why I'm so concerned about this compactification. So here's something that doesn't work. Take a K3 surface and take a non-trivial, by which I mean it's not empty and it's also not a whole space, open size. This view does not admit a logarithmic compactification. Why? Well, if the Poisson structure is going to extend, it actually must mean that the compactification is the K3 surface itself. That's just classification of minimal surfaces. And so you're stuck with the problem that when you compactify, you just have to add in whatever you had taken. But that will never be a Poisson divisor. One of the key features of a Poisson divisor is that the Poisson tensor is always tangent to the divisor. But here, the Poisson tensor is symplectic. It's non-degenerate. The whole K3 cannot possibly be tangent to anything else. Another important example is to do something like this. So take a semi-simple Lie algebra. As we discussed before, its dual is a Poisson manifold. And now you can, for instance, try to take that thing and puncture up the origin. Okay? How can we compactify this? Well, compactifying G check is easy. It's a vector space. You just add a hyperplane at infinity, and that works just fine. The problem is that at the origin, the Poisson structure has a singularity. So here's a picture of SL2. SL2 is foliated by quadric surfaces, which are the coadjoint orbits. And the special one is the nilpotent Hodge, which is singular at the origin. And if you try to blow up the origin, what you'll discover is that the Poisson structure does not lift to the blow up. It has a pull along the exceptional. So it is not, in any obvious way, something that you can resolve. So I don't know what the fix for that is, whether you shouldn't consider it or whether you have to enlarge a notion of resolution. It's not good. In any case, I think there's a kind of message here, which is that in this story, the natural symplectic varieties are like irreducible building blocks. So you should never take a complete hyperkähler manifold and remove some unnatural subset. Any questions about these examples? Okay, so that was the input for the Hodge theoretic construction. You want one of these smooth log Poisson varieties. What is the output? Well, it's actually very simple. We're not going to do very much. We're going to take the mixed Hodge structure on the K theory that we discussed earlier, and we're going to deform it in a very simple fashion. So everything stays the same except for the Hodge filtration, which we perturb by the following operation. So sigma, remember, is a bivector. Which means that I have the operation of contraction by sigma, which will take a form and lower its degree by 2. So this is a well-defined operation on the mixed degree forms, but it preserves the parity. Remember, there's this even odd parity thing going on with K. Okay, so in fact, this is again something which has been known for a long time. I don't know who to credit this with. Certainly, it goes back at least to some ideas that Poisson and Berlinski had a long time ago. But then it occurred in this particular form, for instance, in Marco's thesis when he was looking at the spinorial description of the generalized Hodge decomposition. And Jules made use of this as well. So this is a known thing in generalized geometry. It also has a non-commutative origin, which we'll see soon. Anyways, something important here is that the Poisson bivector, when you contract it, there is absolutely no reason why it should send a closed form to a closed form, in general Lipoma. So this is not a map of cochain complexes. It's just a map of vector spaces. So when you talk about deforming the filtration this way, you can't think of sigma as being an operator in the Coulomb operation. You have to operate at cochain level, deform the filtration there, and then induce a structure on the cohomology from the cochain level filtration. But what's the intuition behind this? Somehow, this deformation of the filtration is encoding some information about the symplectic lead. So remember, a Poisson manifold has a decomposition into these submanifolds that are symplectic. So each one of those symplectic manifolds is two form, which has a cohomology class on its lead. So it has, for instance, periods around cycles and so somehow that's the idea of this F. It's encoding some information, not all, about the periods of the symplectic leads. So here's the first theorem, which is closely related to the Hodge decomposition for compact generalized Taylor manifolds. So in the special case where the Poisson structure is coming, where the GC structure is coming from a Poisson structure, and the manifold is compact. But we gave another proof of this, which just uses classical Hodge theory of Taylor. So there are multiple ways of seeing this. But the fact is that the data of the K theory and the periodized Durand cohomology and this comparison to both the hat class and the wave filtration, which is purely topological, and finally this Hodge filtration. This defines the mixed Hodge structure. It has many beautiful properties. So first of all, it's functorial for morphisms in the sense which I discussed before. And consequently, it's invariant under weak equivalences. And you're always looking at the cohomology of the interior. So that's preserved by these weak equivalences because those are isomorphs. Of course, K theory famously has Bott periodicity, which says it's a two-periodic cohomology theory. But there is a subtlety which has to do with these tape twists that appear in the Chern character. So if you go up in degree by 2, you also have to shift by a tape twist. This was one of the major sources of confusion for me until I got this package. Okay, there's a Poincare duality. So there's a dual mixed Hodge structure, which is like a compactly supported K theory. Various classical formulae for the cohomology of varieties, like the projective bundle formula, the formulas of the blowup, the Thom isomorphism, etc. Those have counterparts in this story. But you have to be very careful about which sub-varieties you're allowed to blow up. But thanks to that, you get a Gaussian long exact sequence, which you recall is a sequence which relates the cohomology of space to an open set in that space and the complement closed, where Z, the closed subset, is a smooth subset. But again, you're going to need to impose some conditions on this submanifold, particularly about the way the Poisson structure behaves in the directions transverse to the submanifold in order to deduce the compatibility of the Hodge structure. Another interesting feature, which again is visible in generalized geometry, but also in noncommutative geometry, is that the canonical bundle acts as a symmetry. So if you take the K theory class of the canonical bundle, that corresponds to the Chern e to the C1 in cohomology. And if you multiply by that class, well, it's an integral class in K theory. K theory is a ring, so that defines an automorphism of the K theory. And that automorphism turns out to be compatible with the Hodge structure, so it preserves the Hodge filtration, which is a non-trivial state. More generally, for certain logarithmic Poisson vector bundles, we can show that the characteristic classes are symmetries of Hodge. In noncommutative geometry, this has to do with this thing that appears in the study of derived categories called the Serre functor, which is an abstraction of Serre. That's symmetry of the derived category. Questions about the state? Okay, period maps. So now we're going to allow X and sigma to vary in a holomorphic family. And the claim, the fact, is that these form what's called a variation of mixed Hodge structures. So I have a family of mixed Hodge structures that satisfy the Griffith's transversality condition. And so these define period maps, which are maps from the moduli space of now smooth log Poisson varieties to the moduli space of mixed Hodge structures. And now you're interested in knowing whether this period map is locally injective. So as Philip explained to us, we should look at the derivative of the period map. In this case, it's related to the contraction operation. So H1 of T, it controls the deformations of the complex structure. Here, T is the logarithmic tangent bubble. It's the vector fields which are tangent to the boundary deposit. And this is the Poisson deformation direction. And anyways, there's an operator given an element here or an element here. You can act on the cohomology of forms by contraction of the vector part into the form part. And that is the derivative of the period map. So if that is injective and things in immersion, then that's actually automatic if X is log Calabi-Yau, meaning the boundary divisor is in. Okay. And so, yeah, that's the conclusion. If this happy condition of injectivity is satisfied, and by the way, in this statement here, there's actually no Poisson structure. This is just a statement about the underlying complex manifold. But then it turns out to be enough to check that condition, and that will guarantee that the period map is injective actually for all bivectors, even ones which are very far away from zero. And the reason for this, again, is this rescaled symmetry. So if I can prove it for small Poisson bivectors, I'm good because I can just rescale. It's an automorphism. I can for big ones, but injectivity is a condition. So now there's a question: how do we actually compute this period? So we're given our log Poisson variety, and we have its K theory, which is a mixed Hodge structure, and we would like to understand in some concrete way what its period is. So what we're going to do is try to take the weight filtration and decompose the K theory according to its weight filtration. So what do? We take the associated gradient. And that, by the very definition of the mixed Hodge structure, is a pure Hodge structure, one for which P plus Q is equal to some definite value J. Okay, so that's part of the data. This associated gradient is some pure Hodge structure. And then we try to fit together K by building up the filtration one piece at a time. So we start with W0, and then we add some more to get W1, we add some more to get W2, and so on. So this gives a family of extensions of Hodge structures. Wj minus 1 sits inside of Wj with quotient jth associated gradient. So it's an extension in the abelian category of mixed Hodge structures. Now there's a beautiful calculation that I guess is due to Carlson, which says that, if you ignore the torsion in these abelian groups, then this extension group is in fact a Jacobian torus. So it's C to the n mod an abelian subgroup. And now here's the fundamental observation. If I take my parameter h bar, which I'm going to use to rescale the Poisson structure, then I get actually a family of Hodge structures, one for every h bar, as I multiply sigma. So I get a family of extension classes, but this is an abelian group. Okay? And the observation is that in many examples, this thing is a one-parameter subgroup. Basically, the reason is that in the definition of the Hodge filtration, you have e to the sigma, like an exponentiation. This is somehow very closely tied up to the fact that as you rescale the Poisson structure, there's a C star action on the h bars, and the Hodge structure, this particular variation, is C star equivariant. And that greatly constrains how these extension classes can vary. So I have looked through the literature to try and find information about C-star equivariant variations. And I haven't found very much, so I wonder if afterwards we could have a quick chat. Okay, so let's go back to the example of the torus. So we have the two torus. It has its toric boundary, which we so take P2 with the triangle. And so what is the K theory? So we have a two-dimensional torus, and we're essentially looking at even cohomology. So that's like H0 and H2, which are both rank 1. So the topological K theory is similarly rank 2 free abelian group. But now we should think in terms of not of cohomology, but in terms of vector groups. So one of the generators for this group is the trivial line. The other generator, or at least the difference between this thing and O, is the deleting line bundle. So this is a very beautiful holomorphic line bundle on C star squared. It is not algebraic. So it does not extend to any compactification. And this is reflected in the Hodge theory. So if you have a class which is coming from the compactification, it's automatically going to sit in weight 0. This class is in weight 2. Zeta minus 1 is a weight 2 Hodge structure. So we get that K0 is the sum of Z of minus 1 and Z. That's these two pieces in its weight. Okay, so here I've drawn a picture of this lattice. And so now I have to look at the rest of the data. So the other piece is the Durand cohomology, 2 periodized. So I have the 0th cohomology, which is generated by the constant function 1. And there's the second cohomology, which is generated by the inverse of sigma, the symplectic form on the surface. And the rule is that as you increase the degree of the holomorphic form, the Hodge filtration degree increases. So it's a bit funny because of the Tate twist. Normally we would think of this thing as sitting in F2, it's a 2 form. But because of the Tate twist, it's actually a 1 form, or it's in F1 in this parameterization. Okay, and so now there's the comparison map. The A hat class is trivial, the tangent bundle is trivial. So it's just the Chern character. The Chern character, the trivial line bundle is the constant function 1. And then the Chern character of the deleting line bundle is determined by its first Chern class, which is this element. Okay, so that's how the integral lattice sits inside the RAM. And now we turn on the Poisson structure, which means that we take this F1, which previously was spanned by the symplectic form, and now we operate by e to the sigma. That's going to take the symplectic form, it's going to contract the bivector and give me a function. It's going to add something in degree 0 forms. So if I write it in the basis given by the integral lattice, what I get is this. There's a factor of 2 pi I, which is a discrepancy between the symplectic form and the bivector. So that appears here. So I get h bar over 2 pi I times the first generator plus the second generator. And that vector spans the F1 part of the equation. So here's the picture. It's some line, which of course need not be integral. But its slope is h bar over 2 pi. So now I look at the extension class. The extension class is basically the obstruction to splitting this thing into 2 lines, which are both integral and compatible with the Hodge filtration at the same time. That can only be possible if this line F1 is passing through one of the integral lattice points where along this vertical line. Okay? And so the extension class is determined by the value of h bar over 2 pi I up to an integral shift. Or equivalently, it's determined by e to the h, which is a non-zero complex. So this is one of the early calculations of these extension groups. Okay, we can do this with these elliptic structures. So you have a smooth cubic, you have a Giesen sequence for cutting it out of P2. And so now what you get is the K-theory is an extension of the first cohomology of the elliptic curve by Z. And so this gives us, on the graded part, the cohomology of the curve, which determines the curve by Torelli. And it gives us an extension class, which is exactly the exponential of this vector field, the automorphism group of the curve. So there's a kind of global Torelli property that the Poisson structure is determined by the function. Okay, so now very quickly, we're going to quantize. So we quantize in the following way. We're going to quantize the structure sheet of the compactification. We're going to do it in such a way that the boundary, the ideal defined boundary, deforms to a two-sided ideal. And so we have an interior which is given by localization. From this data, we can construct a variation of mixed Hodge structure using the formalism of noncommutative, not to be confused with non-abelian, Hodge theory. So this was an idea of Katsarkov, Kontsevich, and Panta, which has been heavily used in mirror symmetry since then. Now there's a huge package of results in the literature on deformation quantization, which allow us to conclude that the variation of Hodge structures that you get agrees with this Poisson thing like this stuff. So the key point is that on the right hand side, we have an invariant which is intrinsic to the algebra, the noncommutative algebra. On the left hand side, you have something intrinsic to the Poisson structure. They have to be the same, and this is the equation which determines the quantization. So we do this for tori. You can see that the quantum algebra has to be these quantum tori that Ernesto spoke about. And now you can calculate, again, you have this extension of z of -1 by z, you solve the differential equation to find the extension class, and this time you find that the extension class is exactly the non-zero complex number q. And therefore, because the quantization has a period which has to match, q is the image. Some closing words. It's been a theme of the week to include something that Nigel wrote in the forum. He wrote that we thus have a general principle relating non-commutative geometry and Poisson geometry with few examples and little understanding how wide or narrow is the world of Poisson manifold, which admit explicit quantizations. Many of you have carefully studied Nigel's papers. I wonder if any of you can tell me where this is written. I thought so. The reason is that it's in the summary of an EPSRC grant, which is publicly available. So you would find it in Google. But it has a special place in my heart because it's what funded my postdocs. Thank you, Nigel.